board, one of the things there is from videos 1 to 4, most everything is there. Um, this problem is one of the problems that is has been. Hang on a second. Um, this is one of the problems that is on your homework. But let's take a look at the homework, and at the same time, let's take a look at. Okay, that's one that I had the video on. Let's take a look at this section. Now, granted, there's probably a portion of this on the videos, so I'm kind of probably repeating myself yet again. But if you consider for a minute that perspective in this drawing, you see something interesting. There's a person at A and a person at the origin, fixed observer, and they're both observing like the movement of this particle. But at the same time, the person at A is not fixed. They are moving. So, for example, if A and the B were moving exactly in the same pattern, it would appear as though, from A's perspective, that B was not moving. So in fact, this position is just a vector addition. Let's see if this erases it. Yes. So it's just simply looking at this from a vector perspective. Here's RA. Here is, and this is an interesting mnemonic or symbolism here. Think of this as the position of B relative to A. In other words, you are A looking at B. And that's all this is. But it's just simply a way of writing this vector equation. Then when you take a derivative, you'll get the velocity in the same way, and you could, somewhere down here, he should have the acceleration at the same, and he does right here. At first, this may not mean much to you, and it is true that some of the problems in the back of this section are kind of menial, so to speak, but let me give you a perspective that actually is useful later, and this is one of the things that if, for example, you had a engine, for example, and this thing is confined to move backwards and forwards. This is confined to move this way. You could list this as A and B and C. However, if you were on B, looking at A, so if you sat right here, and in fact we're looking at C, you would see something different. But if you were at A looking at C, you're at a fixed location, and you would see that C was basically being drawn towards you or moving away from you. So you could list it like this. So, let me see. But if you look at this equation, sorry about that. Um, if you are looking at velocity of A, it is non-existent. So the velocity of B relative to A is simply the velocity of B, meaning this thing is fixed. And that's the case. Now, it turns out later on, this is going to be the key, because we will find out that this basically is an omega r. And there's a vector equation associated with that. And as we move down here, what you'll find is if you look at this, this will rotate. But if you are sitting right here, staring at this rod, it appears like it's rotating under you. So in fact, there is a rotation of this link omega BC. And so as you move down this link, this is the this methodology that you're picking up in this chapter is critical towards linkages. So this little symbolism, you can also look at it like this. If you look at the subscripts, A would cancel. In other words, if you had A times B over A, these would cancel and give you back a B. So in fact, the subscripts are constructed in such a way that you could think of them mathematically in that way, although they don't have that exact meaning, but the symbolism could be thought of in that way. So let's take a look at any particular problem. I know there are some that were in the homework, and they were fine. They are fine, but let's see. That one's in there. Okay, so this sounds, you've probably experienced this before. Okay, a man walks at 5 kilometers an hour in the direction of the 20 kilometer per hour wind. If the raindrops fall vertically at 7 kilometers in the still air, determine what direction the drops appear to fall with respect to the man. So yeah, that's a kind of a boring one. Let's move on to something that is more entertaining. Here, we're in this season. Okay, here we'll just go ahead and select this thing. Shoot. There we go. Okay. Let's just go ahead and drop it right there. And let's go back. Oops, shoot. I didn't hold all the keys down at once. Okay. All right, so here. Move this up. Okay. And might look at this and go on from here. At the instant given, the football player A, this guy, throws the football with a velocity of 20 meters per second in the direction shown. So this is kind of interesting because we're relying a little bit on the information of the past. So it is true the football will have a y component of velocity and position, but the x component of the velocity remains constant throughout. And it's 20 cosine of 60. Do not have, let's see. Uh-oh. Wait a minute. Hang on. I keep going back to the same thing. Okay, there's octave. So in here, 20 times cosine degree 60 gives me 10. I should have known that. Determine the constant speed at which player B must run so he catches the football at the same elevation as at which it was thrown. Okay, so wait, does he start? Okay, also calculate the relative velocity, relative acceleration of the football with respect to B at the instant the catch is made. Ooh, that's interesting. That's a pretty simple one right there. Player B is 15 meters away from A when he starts to throw the football. So what we're going to have to do is we're going to have to come up with this location right down here. So let me go back. So first we have to determine the constant speed of player B. So we're going to have to find velocity of B, which will be a constant. Let's first figure out how far this is going to be. So a couple of ways you could do it. You could recognize that if you put this coordinate right here, where this is x and this is y, then your equations of motion, there is no y naught, so it'd be vy naught t minus, that's a t, minus this. That looks ugly. So let me write it the whole equation. So y is equal to y naught plus vy naught t minus, since gravity does occur in the direction. We have that. Now I can make this statement that says x naught is equal to y naught is equal to 0. Now I'll do this. So Vy naught is equal to 20 times the sine of 60. And unfortunately, I need to go back over here. $17.321. And we're just going to carry that and drop all the digits past that. Now, what we can do, since we have this and that, we're going to look for locations in which y is equal to 0. At what times does this occur? Well, 17.321, getting this, putting here t minus, this is in meters per second, so 9.81 t squared over 2. I can move down and take out the t, and yes, in fact, t equals 0 will satisfy this equation. So this means that that's the point at which he releases the ball. The next point being, let's see, 17.321 equals to 9.81 over 2t. So this would give you the time in which that ball crossed the y is equal to 0 location, being 3, 2, 1. I think I'm still carrying the, and then 2 be approximately. Now, I haven't had any caffeine yet today, so there is a distinct possibility that I may be making a mistake, but that's okay. .53, that's good enough. That's the location that occurs upon. It turns out that if, in fact, these are the 2 times, and there is no acceleration in the x-coordinate, this is 0, so the x, it would be 10 times 3.53, or around 35.3 meters. That's when that ball hits right there. So now, since you already started 15 meters downfield, and this, in fact, is 35.3, that means that this distance, although not to scale, take 15 off of that, take the 1 off, you get a 2, so around 20.3. So he has to run 20.3 meters in that same exact amount of time. So he ran 20.3 meters, constant at 3.53 seconds, gives me the speed of the football player, or the person trying to catch the ball, not just because the other guy's a football player too. 20, oops, 3.53 3 gives me 5.75. 5.75 meters per second. So that means the velocity of B would be 5.75 meters per second. Now, depending on the way you look at this, at what he's asking. Okay, so that's what we determine the constant speed. We've done that. We've done that. Also calculate the relative velocity and the relative acceleration of the football with respect to B at the instant the catch was made. First, let's just do relative velocity. So here's the guy about to catch the football. Here he is. He's looking back. The football is coming to him. He's running. There's his legs moving fairly fast. He is moving exactly to the right at 5.75 meters per second. Football, which I'm going to split it away and say it's right here, but it's actually about to touch his hands, but it's hard to draw the vector there. It has a vector component in which there's a component going to the right at 10 meters per second. Remember that. What is the velocity going down? Because there's still a component going down. Now, velocity of y is equal to vy naught t, minus g t. Let me redo that. G t. So what was my initial velocity? It was 17. There's a way you can check this. 17.321 minus 9.81 t. Now, my t at the point that we're about to hit the guy's hands is 3.53 seconds. So I'm going to do something interesting. Okay, so I'm going to say T O P equals to 3.53. Yeah, 53 divided by 2. Now, what I'm going to do is I'm going to put in that equation. This I'm just checking real quick. 0.321 minus 9.81 times TOP. And so what I've realized, or what one of the things that you realize is, okay, this term almost ended up being 0. In fact, what I'm getting at is, here's the projectile of the ball. This occurred at t is equal to 3.53. Halfway is, 3.53 divided by 2. Turns out the velocity in the y direction at that very top should be 0. So that's a way of checking to make sure you have this equation right, is you go ahead and take the entire time, cut it in half, and double check, make sure Vy is 0. We don't have that, but I mean, we correctly did this, but now let's go back and put in 3.53, which gives us minus 17.308. That makes sense. Actually, the actual exact number should be that in the opposite direction. So I have the velocity of the ball, 17.321. So this is velocity of this. This is weird, but B, that's the guy B. The ball, he's labeling as C. So let's look at this. In other words, velocity of B in a vector form is 5.75. I, the velocity of C, which actually is the ball, is equal to 10I minus 17.321 J. Now, I think you would want to find the velocity of the ball relative to the guy catching it. So that being the case, okay, let's take a look here. That would be, let's look at it from building the equation in reverse order. Velocity of B is equal to velocity of C plus velocity of C relative to B? No, that's wrong. But it is right if you have B and then C here. So if you're looking for this, so what I did is I basically, this has to be in the denominator of the subscript. And so if you look at this, this is velocity of C minus velocity of B equals to 10I minus 17.321 J minus 5.75 I, or the ball looks like it's coming in. Wish they were. Anyway, that's different. Okay. 4.25 minus 17.321 J. So that's the velocity of the ball relative to the player. Now, if we want to look at the accelerations, interestingly enough, the acceleration of the player, he's moving at a constant speed. The acceleration of the ball is only 9.81 J. So if you want to know the acceleration of C equal to and you could use the same thing, pretty boring. Okay, so now if you want to check, I don't know, let's see, I do have the problem number 12234. Okay, let's see if I can find the solutions. This might be a difficult task to do, might be impossible. Okay, that didn't work. It's not listening to me. Okay, I think it's not possible. It would take too long for me to try to search this up, but hopefully everything was okay. I got myself into a pickle here now because this machine is rather slow. Um, I believe I was somewhere maybe right there. Yeah. So at this point, let's see, what time is it? Really, the only other thing that I can give you a guide as far as um, what happens next, and let's do that real quick. Okay, I think that's, let's go down to here. So this, in fact, is week 6. Let's head into week 7 if it's open. If it's not, I'll go ahead and open it. It is open. So let's hit week 7. Um, okay, so week 7 is fairly light. I will be releasing the midterm. There's not many problems here on week 7. I'll be releasing the midterm this weekend for you to start in on. Um, so, let's see. And maybe I'll go ahead and release 8 as well. This thing moves very slow. Here, I'll release 8 and 9. I think it did it. I have, okay, it set it at the very top. Let's see. Uh-oh, that was different. Yeah, 8 and 9. Let's take a look in on 8 and 9. Let's see. Okay, so 8 and 9 are basically very critical in the sense that this is the new material that that is the most interesting in this course. It's basically kinematics, or the beginnings of kinematics of machinery. And this is where I like to focus a lot of the effort. So next week, I would consider to be kind of light, or this week 7 would be kind of light, but week 8 and 9 together will be where most of your new material is going to come from. So I think what I'm going to do, instead of going too far into it, I'm going to basically draw this to a close, and we'll go on from there.